Hi, Diganta.
Hi.
Hello?
Hello. Hi.
Yeah, okay. So, yeah, so seems like it's, the people are slowly trickling in.
Yeah.
As usual, we'll wait.
Yeah, I joined like 5 minutes early, I guess, today.
So, how are your other classes going? I mean, in terms of how the online lectures, they're all going
So,
okay.
yeah, they're all going quite okay. So, I mean, other than the MCSV and SMT4DL, the only other class I'm having which is like taking online regular classes is proofs and types.
What was that?
So
Proofs
basically,
and proofs
proofs
and
and types.
types.
Yeah, proofs and types. Yeah.
But so you're taking, in your case, you're taking only 3 courses there?
No. I'm taking two other courses. One is DMML, and
Ah,
the
why do you say that that is not online?
no that they're taking online. So the way that course is working is instead of having each lecture online live like our courses are, they're
Oh, they
uploading.
pre-record.
Yeah, they're uploading pre-recorded videos, and then we're having like a discussion session once every week.
Ah, So you can watch at your own leisure. Huh?
Yes, yes. And then when we like have questions, we come to the discussion sessions.
Hmm.
So, and the other course, other than that, I'm also taking the quantum computing course.
Ah, okay. Well, 5 courses, isn't it?
Yes, yeah.
A lot to handle.
It is. I mean, well, initially I thought like, it would be fine. Now it's okay, but like I think I can manage.
Okay. So I think I will start. Okay. See, this is the first time I'm teaching online. I mean, I usually use slides in my lectures, but fully online. So I wasn't, so I myself am not sure because see, I can't use the board, and for a lot of these pictures,
Yeah,
so I'll have to uh, spend a lot of time. And I'm not sure. Sometimes overuse of those things can be a little bit daunting. So I appreciate feedback, okay, as
right.
to
I
what
think
how I can improve and so on. So it's a small class, and I don't mind getting critical comments. That is one, and the other, yeah. So the other thing is this part of this fixed point theory part.
hmm,
I'm going delving. This is the first time that I'm delving more into the theory. Okay, I usually do that, cover that, but somewhat in a very sketchy fashion. For example, I don't go through proofs of Tarski's theorem or even Cleanest. Sometimes I'm not going to discuss Cleanest theorem. I mean, and that's partly because sometimes we've combined a lot of these automata theoretic thing with this. Then we just don't have the time. Okay. So this time I consciously made a decision as I had indicated. Oh, sorry, I had to record it. Um, yeah. Um, oh, yeah. So this part is certainly some thing new and going through the first time. So I certainly would appreciate if you could bear with me and also give feedback. And certainly these things that I'll be discussing later on, like predicate abstraction and the inductive model checking, especially the IC3 part, they are also I'm doing for the first time in the class. So there is, I have made a deliberate decision to do more of the symbolic model checking, for which I believe that it is important to understand this theory. And that's why after having spent significant time going through the proofs, I want you guys to recreate this proof for a couple of do these kinds of proofs for a couple of other things as part of your assignment, so that
yeah,
things will be clear for you as well. Now, of course, as you know, the significant part of the exercises, problems, etc., it's in implementing these algorithms. Yes, there'll be some quizzes where I will ask some basic stuff, but it is in the written exercises, the one that is going out where I'm thinking of making you do some hand proofs. And therefore, it is important that you try to understand, or even if you don't understand, give me feedback so that we can all I can make corrections and do the stuff. Okay, so don't be hesitant or shy of expressing your doubts. Okay, so let me start. Okay. So summary of the last class. So we are concerned with fixed points, and the fixed points that we are interested in are those of what I call as predicate transformers. These are functions over sets of states. The functions map formulas. You can consider these formulas denoting Boolean functions. I'm sorry, this should have read 2 to the s. So the domain and the range of the operator whose fixed points that we are interested in are the power set of S over S, where S itself is the universe of states of the Kripke structure on which that we are interested in doing model checking over. And so when we talk about fixed points, fixed points, the underlying domain for fixed points of functions, the functions are complete, are partial orders. And we have a complete partial order. A complete partial order is one which has both the top element and the bottom element. Here, the elements of this domain, the complete partial order lattice, are the subsets of this set of all states that are part of the Kripke structure. And a complete partial order requires a partial order relation to order the elements of the lattice. And here we use the subset relation over states. Now, tau will be a basic function of our model checking algorithm, which will be defined in terms of T, the transition relation of the Kripke structure. So that's how the connection gets established. And fixed points of tau will be associated with the CTL operators, and with fixed points denoting actually the states, the set of all states satisfying a CTL formula. Okay. And that's how we are defining, and that's why you should see this connection between model checking, as certainly for CTL model checking, and the relation with fixed points. So we saw 2 important theorems related to the theory of fixed points. One was Tarski's original fixed point theorem, the earlier fixed point theorem. This one guarantees existence of and uniqueness of fixed points for as long as tau is monotonic. Okay? And that serves us quite well because the tau that we use for model checking purpose, they usually accumulate states, or they can dissipate states as well. So those are 2 ways of doing. And when tau satisfies the monotonicity property, the fixed points also satisfy quite interesting properties, and that's why so that we exploit in this thing. So both Tarski's fixed point theorem and the second one, the second theorem was that of Kleene and Tarski attributed to them, which allows a specific way of computing these fixed points, specifically by iterating over tau chains, either starting from bottom, which is false, or top, which is true, which, so denoting all the states. So that's the difference between them. Both these theorems are applicable for infinite domains, okay, as long as tau and for functions that as long as they satisfy the monotonicity property, and in order to be able to compute this as the limits of tau chains, an additional property was required, which is required that the function to be continuous. Okay. We'll see CTL model checking will be different versions, usually optimized implementations that use Kleene iteration. Now, and the reason the importance of these understanding these fixed points comes if you really want to prove correctness of these model checking algorithms. Okay. Now, yeah, so it is always good to understand some amount of theory. And since this is based on logic, although you may not be asked to do a lot of correctness proofs, at least you should be exposed to how one goes about verifying or establishing the correctness of these algorithms that we are all studying in this course. And and that is the my intention here. Okay, any questions so far? Okay, so I'll proceed. So what I want to do today is kind of go through some clarifications that I thought of some things that I was not too happy, and some clarifications on certain points that I made that I wanted to, that needed some corrections. Okay, and there were also some mistakes on the slides that I want to correct. And as I promised, I will go through a proof of Tarski's theorem. Okay, this proof is also given in the textbook, and I have done a little bit of cleaning up of things. The Kleene-Tarski version of the theorem, which we saw last time, that one is not the way it is. A proof is there in the book as well, but I found another reference. I mean, another thing. It is actually on a Wikipedia proof that was in Wikipedia. I will include the reference to that in these set of slides, so you can do it. I found that better than the proof that was there in the book, and that's the sketch that I followed last time. And we will also, as promised last time, I'll go through a proof of correctness of the fixed point computation of the fixed point formulation for one of the CTL operators, the EU one. Okay. And time permitting, I will give an introduction to BDD, which is what in your first programming assignment you will be using to implement this model checking procedure for CTL, for CTL using the Kleene iteration method. Okay, so I'll start with Tarski's fixed point theorem proof. Okay, so there was one question last time, that one, I don't know who asked, more like a comment, okay? So I kind of introduced these prefix and postfix points as though, and an alternative characterization of the greatest and least fixed points of tau, as though that was the definition. So there was this question, why isn't fixed points just has a simple definition? X is fx is equal to x. X is a fixed point of function f if fx is equal to x, fx is equal to x, and then you just take the least of all those functions in the CPU order. So that is correct. Okay. So I should have, in the slide that I had defined it as definition, I think I think, who was, by the way, who was the person that made the comment? Is he here? Hello? I'm trying to give you credit. If you respond. Hello?
Sir, what is the thing?
No. Someone pointed out while I put up a definition of, I put it as a definition, okay, of greatest and least fixed points in terms of the greatest and least lower bounds, the greatest, least upper bound and greatest lower bounds of the set of things introduced as prefix points and postfix points. I introduced that as a definition of least and the least fixed point and greatest fixed point. And then there was a comment which was made, why is this a definition? I mean, isn't there a simpler definition? A fixed point is a fixed point. And the least in the ordering is the least fixed point, greatest fixed points. I think that is correct, okay? So this, I should have given this as, I should have introduced this as another alternative characterization of least and greatest fixed points of monotonic functions that is used in Tarski's proof to prove the existence and uniqueness of fixed points, okay? So that's why this proof actually shows that this way of characterizing indeed in terms of greatest lower bounds, least upper bound and greatest lower bounds, it assists in the proof, okay? So that's why I was giving credit to the person who made and observed that comment, okay? Yeah, that was my comment. Okay, so if tau is monotonic, okay, here's what, look at this example, study this example, or another one that I will introduce, okay? So so Tarski's characterization, at least in his proof, he introduces what are called prefix points and postfix points, okay? Prefix points are, the set of all elements in the lattice such that Z, tau of Z is less than or equal to Z. Those are prefix points. And you say in this, actually you just pick states where tau is going downwards, okay? And since it is less than, fx is less than or equal to Z, it also includes, these sets also include the fixed points. The postfix is those set of points in the lattice where tau x is greater than or equal to Z. Okay, that is, so they are the points where you look for those kind of states in upward chains. So an important observation in terms of fixed points, and as so here's an example. So in this example, so what are the post-fix points are, you look at post-fix points, you look at all the downward chains, okay? So it'll have all the fixed points. Okay, by the way, there is one correction here. There's an arrow missing from 1, 3 to true, okay? Assume that there is an upward arrow from the set 1, 3 to true, okay? So the set of all post-fix points are you look at the upward chains. So, here the three fixed points are top, the set 2, and bottom. And 1, 2, and 1, 3, the set 1, 2, and 1, 3 satisfy are the cases where Z is less than or equal to tau of Z because it's going up. Okay? So the set of prefix points are, look at downward chains. So 1 and 3 are included here. And of course, all the fixed points, because they do satisfy this condition, all the fixed points satisfy this. So Tarski's characterization is as follows, okay? Says, you take the, finds the least fixed point of tau as the greatest lower bound of all the prefix points. And the greatest fixed point, GFP of tau, is considered as the least upper bound of all the post-fixed points. Yes. Okay. You don't get confused this with Kleene thing. So here, the entire exercise of Tarski's version is to just define it as greatest lower bound and least upper bound, okay, of certain kinds of sets. Here, in this case, prefix point and postfix points. Whereas Kleene's version is to come up, compute it as a chain. So that's why here this is a more general characterization of the that is useful to show the existence and uniqueness of greatest points. And this doesn't require the assumption that the functions have to be continuous. Okay? That is limit preserving that Kleene's version requires. Really, this way of characterizing is with the, and when you see the proof, you will see this thing. So the proof itself, every step of the proof, is quite convincing. Okay, and it's a fairly small proof. It's not a, very big proof. But the intuition behind this thing is, if it is for any monotonic function, the fixed points reside only on tau chains that are either downward or upward. Okay, so you can only look at them. So here, for example, as I said, the greatest fixed point is the least upper bound of all post-fixed points. So the set of all post-fixed points is here given. So taking the least upper bound of this set as postfix means you have to take the union of that. Okay, since top is there, so top is the greatest fixed point here. So you get top. The least fixed point is given as the greatest lower bound of all prefix points. The set of all prefix points here is, and the greatest lower bound is computed as using the intersection operator. And so bottom here is taking the greatest lower bound, that is taking the intersection of all these sets, will give bottom, which is indeed the least fixed point top. As a result of this observation, you see another thing is the fixed points themselves form a lattice. Okay, so you can see there are 3 fixed points here, and they, that is a consequence. That is true for all monotonic functions. Okay, this observation doesn't mean that tau chains don't allow, I mean, all chains in a, when tau is monotonic necessarily have to be upward and downward chains, okay? So I'll give you an example, to show that that doesn't have to be the case. Is this visible? So look at this example. Here, there is a kind of this a chain which just goes sideways here, but there are things, and it still has greatest and least fixed points. So that's why, yeah, so this is a case where it is still tau is monotonic and there are things, but you can, what Tarski's characterization says is that you can actually, you only need to look at this portion of the thing which only consists of the upward looking and downward looking chains part of this lattice, and then get the post-fixed points and the set of all post-fixed points and prefixed points there, and then you will yeah, so to get the fixed points, okay? So that's the observation, okay? So in that, this thing will be used in the proof. Oh, shoot. That's not what I wanted. Oh. Okay, so so there are other examples. You can go through these things. So these examples here, I mean, you can compute the postfix and the prefix points, and you will see. See what another observation that will give you a better understanding of Tarski's theorem is what the saying is that when you take the set of all prefix and postfix points, look at this example in the center is of interest. Now here, so whenever you have two incomparable elements like set 1 and 2 as fixed points, so you will see that you will also need to have its the greatest, its upper bound, the least upper bound also as a fixed point, okay? And what Tarski's idea is doing is he's collecting all these things, okay? And this is true. So whenever you have incomparable things, if tau is structured such that is defined such that there are two incomparable elements, then you take all these things and in this case, the least upper bound and the greatest lower bound, they also have to be, in the, I mean, the existence is guaranteed. And when such incomparable things are fixed points, then it's the lower bound will also have to be fixed points, unless they are chains that are actually going. Okay? So, and that will be quite clear when I go through the proof thing here. So is this clear how Tarski has characterized? See, when you define this thing as the greatest lower bound or least upper bound of certain subsets in the CPO, then it is easy to show the existence and the uniqueness, because one of the properties of a CPO is that the least upper bound and the greatest lower bound are guaranteed to exist for every subset of the domain, and they're guaranteed to be unique, okay? And therefore, this existence and uniqueness follows, okay? And the proof of Tarski's theorem just consists of showing that indeed the greatest lower bound and the least upper bound of these sets are indeed fixed points. Okay, the moment you show that, then and they are proof of existence is already given. Okay, so that's what the proof. Let me go to the proof anyway. Okay, so that will, yeah. So this is what pictorially what the implication of this defining this kind of characterization has. So you only, as I said, only need to look at that part of the lattice where the tau x is less than or equal to x, or x, tau x is greater than or equal to x, okay? So the fixed points do not exist. This is the only place where you can have the fixed points. So all this set, upper set here is the set of all prefix points, okay? So where there are all the downward going chains, and this, the set at the bottom here is the set of post-fixed points, and they intersect. So if you take away the other kinds of chains, in this case, there's no sideward going chain. So you only need to look at this part of the domain to look for your fixed points. And Tarski's characterization says that, and the intersection of these two sets is where all the fixed points for tau lie. Okay, the greatest, the least upper bound of that, yeah, of this post fixed points forms the greatest fixed point of tau, and the greatest lower bound of all the prefix points forms the is the least fixed point. Okay, so that is what the observation and the proof will involve. So these two sets can never be empty. Why? Because of the existence of top and bottom, okay? So, this have to include, if either there are, fixed points here, somewhere in between, or, if there are no other elements for which tau x is less than or equal to x, x is less than or equal to x, that is not possible, because then eventually top is the the highest point, and therefore if there is nothing else, at least top has to be, okay? Similarly, bottom is less than everything else, okay? And if there are only two elements in these postfix and prefix points, top and bottom, and they have to be the least and the greatest fixed points. Okay? So existence, as I said, is obvious because this is not empty. If nothing else is there, it'll definitely top will end up being there. And by the property of CPO, the GLB and LUB of any subset of elements are unique. Okay, so all we need to prove is that this the least up, the greatest lower bound, and the least upper bound of these two sets are indeed fixed points. So here is the proof for the GFP case. Okay, the greatest fixed point case, and you can do as an exercise for the other, the least fixed point case by looking at. So for this, we look at post-fixed points. This is because it is the greatest, it's the least upper bound of this post-fixed points here. Okay? And that's what we're looking at. So the claim is that the greatest lower bound, that is the union of all the post-fixed points, is the greatest fixed point of tau. Yeah, that's what we need to prove. And so we need to actually prove if P is that, the least upper bound of all these post-fixed points, what you have to show is tau P is equal to P. Okay? And that there are two parts when you show this, that P is less than or equal to tau P. The other part, tau P, is less than or equal to P. So that's the two parts. Any questions so far? Okay. Here's the first part. So by definition, yeah, no, I'm sorry. They are so P is the union of all the elements in this, of all the post-fixed points. Therefore, every element in S post must be less than or equal to P. So the moment Z is less than or equal to P, by monotonicity of tau, tau Z will be less than or equal to tau P. Now, Z is already less than, because this contains all the elements in the domain where Z is less than or equal to tau Z. So we have this relay. Yeah, so by this, tau Z, and by monotonicity, tau Z is less than or equal to tau of tau Z. So tau Z itself should be in S post. Okay, I'm sorry. Sometimes I've used S post and sometimes I use S post fixed. They mean the same. Okay. Since tau Z itself is inside, must be inside S post fixed. So we have this for every element in Z inside this set of post fixed point as post. This relation holds good. Okay. But P is the union of all elements in there. Therefore, and since for every Z, tau Z itself is in there, and P is the union of all those things, you know, P must be inside, must be less than or equal to tau P. Okay, so that's how, you know, you get that part of the relationship. Okay, any questions? Okay, the second part is fairly simple. So once you establish that P is included in tau P, and this satisfies this definition. So P should be in the set of post-fixed points as well. So tau, and if P satisfies this, tau of P by monotonicity should be there as well. So, and so it should be, by monotonicity, we get this relationship. And because of this, it follows that tau P should be in P. And since P is the union, so you get tau P as less than or equal to P. Therefore, the least upper bound must be a fixed point as well. And that's what I kind of observed. I mean, where you have, okay, see, yeah, and if that's why if you have two incompatible elements being themselves being fixed points, you will have to have the their least upper bound and the greatest lower bound also as fixed points. And since these results are applicable to infinite domains, so without continuity, tau, even though it may be monotonic, if the domain is infinite, the tau may not be limit preserving. That not all chains may have limits. Okay, that's another case where it's the greatest lower the element that is greater than that will have to take over. Okay, because without continuity, these monotonicity doesn't guarantee limit preservation because of the Zeno effect. Suppose when you have real numbers, there can be infinite number of real numbers between any two real numbers, and therefore, that's why you need this kind of an argumentation, without relying on chains. Okay, and if you rely on to show the existence and the computation of fixed points by only looking at downward upward chains like Kleene iteration does, then you require continuity. Okay. Okay. So this ends the proof of Tarski's original theory. Okay. I may say original because Kleene did that. The other one a bit later. Although these are all very, very early 1950s and so on. But Kleene iteration is very important for logic and foundations of computer science, because almost all the semantics of everything that you see in big part of computer science, they are all in one way or the other expressed using fixed point theory. Okay, so now this is the end. So then the other, so any questions so far of any general, specific, or anything? So as an exercise, I would want you to just to make sure that this steps are sink into you. Try the proof for the LFP case, getting a proof for the LFP case with the same level, at the same level of detail. So that will be instructive, and I might even assign that as one of the problems in the assignment. Yes? Was that a question? I heard some sound. Someone speaking. If not, I will move forward. Okay. So this we already saw. So what I want to do next, this is the Kleene fixed point theorem. I'm going to skip all these characterizations and then move directly to this part. So we saw the characterization or the definition of the set of all states represented, satisfied by formulas, various CTL formulas expressed by different CTL operators at its root as either a least fixed point or a greatest fixed point of a suitably defined tau. And for the case of F1 until F2, EF1 until F2, the tau was this one, okay, which started with by including the set of all states that satisfy F2, and in each iteration you add those states that satisfy F1 and lead to a state that you have already computed. And there exists a successor from that F1 state to something that to Z, and the fixed point of that. And the least fixed point of that is what you get will be the set of states satisfying EF1 until F2. So remember, EF1 until F2, the way we defined in the formal semantics was as a inductive relation. We defined it kind of inductively. We said F1, we include F2, and then we define, the way it was defined was by looking at paths originating from states on which F1 satisfied, parts which had F2 eventually being satisfied at some point, and all the way up to that point prior to that, F1 had to be satisfied. So, and the smallest relation that generated those sets was how it is defined. So this is the proof itself. I mean, one thing is for you to understand informally, intuitively, what this means in terms of clean iteration, which the picture does, that is necessary for you to implement. For the proof, you will have to define, the proof consists of is one which relates one way of computing this least relation. On the right side, you have a tau chain, the clean iteration. On the left side, you have the way that the formal semantics of satisfaction was defined, in defining the semantics of CTL operators, and you have to relate the two things, okay? And that's what the formal proof of equivalence does, okay? And, because tau is monotonic, and is clear. So every time when you're asked to define a fixed point to do something, some variation of a model checking algorithm, the first thing, if you want to rely on clean iteration, the first thing you have to ensure is that you have to make sure that whatever tau that you define in order to design that thing has to be monotonic. And since we are only dealing with finite state systems, monotonicity implies continuity, and therefore you can use clean iteration. So what you have to prove is two things. One is that the least upper bound of all the sets that you just get on a Kleene chain is a subset of the EF1 until F2 as defined by its first principle semantics, and the other way around. And that's what I'm going to show as a proof. So this one is, here you use induction, much like the proof of the Kleene iteration, which showed that what you get by taking the least upper bound of a Kleene chain is indeed the least fixed point. And there we showed it that by showing it that it was less than or equal to any other fixed point. Okay, fixed points, any arbitrary fixed points, by using induction on the length of the Kleene chain. That is by showing that for every I, in n, the natural number, for tau I of bottom is included in EF1 until F2. So that you can do some very similar to that proof. Therefore, first I will do the second part first. Okay. I might show you this first part also if I'm not running out of time. Yeah, that's the first part, and that has to be shown by induction on the length of the Kleene chain to the the least upper bound. Ooh, what happened? So this, the second part, in order to show that here, this is a little bit more complicated. Okay, by induction on the length of the prefix of the path under which F1 until F2 is satisfied for S. Because here you will have to take recourse to the way that the semantics of the CTL operators were defined, okay, by the first principle semantics, okay, because there you use the paths, okay, paths originating from various states, okay. So the induction is based on the length of the path that the formal semantics will require in order to show the satisfaction of that particular formula. So that's the proof. I'm sorry. Okay. Yeah. So I have the details here of the second part. So what I mean by that is for every state that satisfies, yeah. So E of F1 until F2, the semantics of that was defined. The satisfaction relation was defined by saying that there should exist a path of this form S1 when S1 is equal to S going all the way to Sj, such that Sj satisfied F2, and every state from S1 till Sj minus 1 must be satisfying F1. So the induction is on the length of this prefix J, okay, in this case, that is required to show the satisfaction of a particular state. Yeah, here the first part, it is on the induction on the length of the tau chain. So that's the induction that's used here. So the base case is where, so for each of them, what you have to show is, yeah, so here, this is what you have to show, okay? You have to show, existence of some I value n for, that, oh, there's a mistake here. What did I do? Yeah. No, this one should have come here on top of the cup, okay? One is sitting here. Please, there's a typo here, and the one should be I is equal to 0 to 1 is what it says, okay? So, so for the case where the satisfaction for the state can be shown by just with j is equal to 1, which means the prefix is 0 here, corresponds to the Kleene formalization corresponds to where I is equal to 1. Okay, so I is equal to 1 case is where you have tau applied to bottom, which is false, and that is equal to tau with I is equal to 1 is tau bottom. So this reduces to F2, the base case, F2. So we have to show F2 is a subset of tau of bottom. So that is, bottom is false, and that means that tau will be expanded from its definition to this. And since Ex of false is false, you have F2. Okay, so F2 is less than or equal to F2. So the induction case will assume this claim holds good. The original claim holds good for every S and every J less than or equal to some N, okay? And then what you have to show is that it holds good for those states which require, whose satisfaction, the length of the satisfaction prefix from that state is of length N plus 1, okay? That's what you have to show. But you, as induction hypothesis, you can assume that for all states whose prefix length is less than or equal to N for satisfaction, to show satisfaction, that this claim will hold. So let S1 be such a state which requires the prefix to be of length N plus 1, okay? That means there is a path from S1 to Sn plus 1 such that Sn plus 1 satisfies F2 and S1 through Sn satisfies F1. Now you have to show there exists a value of I such that S1 belongs to tau I false. And that's how we do okay. So, and by hypothesis, there exists an n. So there exists an n for showing for S2, no? Because S2, from S2, the prefix, the path of the prefix, the length of the prefix for that, the path of satisfaction is n. Therefore, I'll be using the induction hypothesis. Induction hypothesis on S2. Okay. So which means I'll assume that S2 there exists, for tau of n of false, S2 belongs to that. Okay. Now S1 and S2 are related by the transition relation of the Kripke structure. And tau of n, so and therefore S1 is actually, S1 is a state that satisfies F1 and leads to something, to an S2, which is contained in tau of n of false, okay? And so simply you're extending it, and therefore S must, and this is exactly what you see on the right side of the turnstile here is exactly tau of n plus 1 as per the definition of tau, okay? And therefore S should belong to tau of n plus 1. So that's what the thing. So these are, I think, these steps are, proof of the step are, needed for you to keep you honest, okay? But you should also see the high-level proof structure of how the induction principle is being used, and then you expand tau, and then you use the first principle definition of the semantics of the CTL operator. So these two are relating those two things. Okay. Okay, so any questions?
Yeah, so the definition of tau z, that is, like, we don't want to, at the end of the day, express it as a CTL formula. We want a positional formula, right? So we'll probably have to, I mean, in this case, we can expand out EX as something in terms of like the transition relation and states. But in general, will this not be a problem?
No, when you're implementing, this is just a proof of correctness, that's all. To show that it corresponds this way. You're using in your implementation, all model checking algorithms, they use clean iteration. Okay?
Right, so I mean, in the implementation, tau z will not be defined in terms of EX, right?
No. It will be defined in terms of EX.
I mean, it will be semantically equivalent to that, but like it will be encoded in some other way, right?
Yeah. I mean, I already showed the encoding for EX, no?
So it'll use that itself. So
Yes.
in general, for EX, that's not a problem. But if you had some other quantifier there, then I mean, we cannot define taus like that and work with them in this way.
No. As long as tau is monotonic with quantifiers. Quantifier is an orthogonal issue. Okay.
Yeah.
So I mean, yeah. So as long as tau is monotonic, and then you have a definition for the tau.
So if that definition, say, involves something like EG, then we will, I mean, then that would become a problem.
EG is also was expressed. If you look at the tau formula, tau representation for EG, that also had EX. Only EX.
Right, exactly. Okay, yeah, fine.
Yes.
Yeah, exactly. Yeah.
So what you will have is, so even in the implementation, you will have EX, okay? all this is doing here is on the right side, it is expanding the taus out, which give rise to the whatever the definition of F2 is. On the left side, what you're doing is you are, doing the usual thing of what are the parts, from originating from the state and so on.
Yeah.
The reason that I needed to use this T was because then I could, this EX really contains T inside it, okay? Remember that, okay? So that is why this T was important to observe that S1, S2, going from S1, S2 is from T, okay? I mean, uses T on the semantic side, which is what is used here inside EX to do the T. Otherwise, you don't get that this one thing. If the EX was defined in terms of some other T, and you was using some other T, that this won't work. Okay.
Right.
So inside EX there is an embedding of T, which is exactly the same T that it was used. Yeah. Any other questions? Yeah, I think, the first time, even if you don't understand, I mean, I think you should go through the proof and the best way is for you to recreate it for another one. As an exercise, what I'm planning to do is for you to recreate this for the R operator, okay? And that I'm thinking of giving as an exercise, okay? So let's see, so that, no, I want to skip the first part of the proof because that is very much like I have produced here. I'm going to upload these slides, compare that to the proof of Kleene showing the Kleene-Tarski's theorem. It's very much like that, okay? So this is for all the CTL operators, okay? I'm not going to go through each and one of them. I've already gone through EG and EF, okay? So first is you already have these taus defined here. All you have to do is to convince yourself through examples and so on that indeed informally convince yourself that how you how this expands out.
Sir,
Yeah.
sir, I know an efficient way to compute EX of Z. You just take the predecessors, right?
You just take the predecessor. That's, yeah. What? Yeah. I mean, yes. EX is taking the predecessor. Correct.
Then what is the most efficient way to compute AXZ?
Yeah. For AX, see, for EX, it is AX can be expressed as for all. Okay. Or the negation of exists. Okay. So I think the most efficient way is to just reduce them to one quantifier, all existent quantifier, okay, and then do existent.
Just going through all the states does not make sense, right?
Going through all the steps means what? What do you mean by all the steps?
Not steps, states.
No. See that if you use that is exactly what I'm pointing out here. Okay, so here you are. I haven't gone through any particular example. See, but what you end up doing here is in one step, whereas the explicit state approach operated on the graph, okay, on the graph structure. So on the graph representing the transition systems with nodes representing the states and edges actual thing. So there you would end up enumerating all the states, whereas here, in one step of tau, you could collect a whole bunch of states, okay? That is why sometimes this can be a winner, okay? And most times this happens to be a winner. So you're right, in that sense, when you said you don't need to go through all the steps, I presume you're comparing it with the explicit state approach. Am I right?
Yes, sir. Yes, sir.
Yeah, that is avoided here.
This is supposed to be efficient and that, right?
Well, no, let me be careful. Let me be careful. Say efficiency average efficiency is different than worst case efficiency. The complexity here is also the worst case complexity cannot be. It cannot be any better. As a matter of fact, worst case complexity, I mean, I'm not going through all the things. There is a little bit of, there is a quadratic thing here, okay, on the states. But, you know, so even if assuming that it is the worst case complexity is the same, efficiency means what works in practice. Okay, the worst case complexity is the same. And yes, the time complexity. So there is a, yes, because you are, yeah, so on an average, because you getting to you know, accumulate lots of states in one step, the convergence, the number of iterations that you will have to do might be smaller in this case. But there is a price you're paying. You're using more space because your formulas that you get, because every time that you use a tau, you're introducing an existential quantifier. Eliminating that in a naive way will give rise to explosion of formulas. Okay? So there are two ways to do that, okay, to avoid that explosion. I mean, one of you asked that thing in the first assignment, or if I can I express the existential quantifier, or if I have to expand it out on bit vectors, it gets too you know, too cumbersome into thing, and you can see that it does. Okay, but if you want to reduce it to SAT solvers, you will have to eventually do it like that. Oh, but there are other approaches. Okay, we will get to that. Okay, without actually introducing quantification, but nonetheless, the way this fixed points, if you really want to compute this, you have to worry about how to do a existential quantification elimination. That's the pre-image computation as efficiently as you can. There are two possible things. One is we'll be looking at the BDD thing, because BDD forms, there you can eliminate the existential quantification in linear time. In linear time, this the size of the formula, and BDD sometimes can be an enormously compact representation for formulas, okay, rather than the CNF form, which is what is used by SAT solvers. CNF form, I mean, SAT solvers, for you know, good reason, they use CNF form, whereas BDDs use a different, if there else form, decision tree form. Okay, that is one approach. Okay, or you can keep the quantifiers, don't eliminate them, then directly use QBF solvers. Okay, we won't be covering QBF solvers, but I gave you Z3 already supports QBF solvers, and I showed you how you could directly keep the quantifiers in your formula and then invoke the quantity, not reduce it to quantifier-free Boolean logic, but keep the quantifiers and you can use QBF solvers. I mean, people use QBF solvers, worst case complexity is even worse than SAT solvers, which is NP complete. But a lot of advances, you know, engineering advances in a QBF solver makes it possible. So an interesting exercise which is always wanted to assign is, instead of using, I've usually assigned as programming assignment using BDD to do it. It would be interesting to use QBF and see how efficient it's Z3. Z3's QBF solver is not the most efficient. You will have to use more state-of-the-art QBF solvers. So those are two, when I say efficient way of doing it, that is two approach. The other thing which we will see, which I will cover in the class, is there are certain ways of transforming your transition relation, partition your transition relation. This works especially when you're composing concurrent, you know, different modules. You, based on the occurrence of variables, you can decompose, you can partition the way you express your transition system so that you can move certain variables out of these existential quantifiers if you partition the way that you define your T. And that gives you a lot of mileage. Okay, in either of these two approaches that you can use this partitioning of this thing, where you remove certain variables outside the scope of these existential quantifiers in order to save the thing as a pre-processing step. Was there a question? Okay, so these things we will look at when you do some implementations. I will cover these as small engineering ideas. Okay.
So compared to explicit, like checking over, say, states, so there we have to keep track of all those explicit states as well. So that is going to be very heavy on the memory, right? I mean,
that's why I said most implementations, if you want to check something, do a Google search on spin. That's one of the most successful explicit state model checker that is there on the planet. Okay, I mean, there are various versions of it. I mean, I'm going out on a limb here. That was certainly one of the earliest one. The author of that is one Gerard Holtzman. He is a professor at Caltech, and he also works for JPL. But again, anyway, that's history. I mean, that's part of historical information. He used to be at Bell Labs. Spin was developed when Holtzman was at Bell Labs, and they used, even to this day, Bell Labs uses that for a lot of, verifying their communication protocols, distributed concurrent communication protocols. But that aside, there was this question, okay, as to don't you need to construct this whole thing? Yeah, if you try to construct that a priori, it will not be successful. Okay, it uses on the fly. It constructs this in a lazy fashion without having to represent in your system the unreachable part.
So does that achieve less in memory than even symbolic model checking? Or how does that compare memory-wise?
Yeah, I think for certain kinds of application, you have to throw away a lot of things. He throws away a lot of things and said, these protocols, if you're verifying things at a very, very high level, okay, where you're not doing real design or code verification. For code verification, it's impossible, okay? You can't do that. So here, when I say protocol verification, you have very high level skeleton of that protocol, but still those protocols are very, very, very hairy, in the sense they're very, it's not easy to figure out. I mean, you must have heard of Byzantine protocols.
Yeah.
For example, now Facebook, Google, etc., they're very interested, especially with the blockchain, becoming very more and more popular. All these things of attacking under different kinds of faults, malicious faults, etc. They're very complex algorithms. They are called Byzantine fault-tolerant algorithms. So you could verify those kinds of protocols at a very high level. And I think some people have tried to use model checking. Now, even then, I didn't answer your question. So I think at a very high level with all the engineering, I think you could do. But if you ask me, head-to-head competition, where symbolic model checking versus explicit state, I don't know, with SAT solvers, ruling the roost, I think it is, I would say even for those high-level things, model checkers are becoming, symbolic model checkers are outperforming those things. But for certain class of applications, it can be a toss-up.
Right, so that is both in terms of speed and memory. So.
Correct. Yes. I mean, see, the bane of the symbolic model checking is always the thing. Spin uses a lot of hashing and so on to keep very smart things saying, oh, this part is not covered and so on. Frankly, I have not studied explicit model checking's implementation issues that well. Okay, So I'm not the, I mean, I can't give definitive answers here. Okay. So yes, I would, I mean, let me put it this way. Most of the research, okay, there is this something called partial order reduction, okay? Without using partial order reduction technique, and I don't want to go into that, okay? That is, without using partial order techniques, explicit model checking, explicit state model checking does not work, okay? I mean, it is just not even possible. But with partial order reduction, for certain class of protocols, explicit state model checking can do. So partial order model checking, the idea is really, yeah. So maybe I should, yeah. I mean, I wanted to finish something. Yeah. So maybe I will talk a little bit. So you know, with a lot of these traces are not even are redundant to prove certain safety properties, okay? Especially, for example, in concurrent systems, in asynchronous concurrent systems, usually you have to consider all kinds of interleavings. But you know, if you do A and B could be two non-deterministic, the order doesn't matter. So you have to consider both A after B, A before B, and A after B, okay? And you keep doing this, you know, and the interleavings can explode. So if indeed you can a priori determine that A and B are independent actions, where A and B, you know, the order, regardless of what order you do, you end up in the same state. Okay, they are called independent actions. If your transition relation, in your system, you can identify all independent actions, then you can enormously reduce through this techniques called partial order reduction your interleavings. Okay, then those kinds of techniques have to be used. With that, it can be competitive. Okay, is what a proponent of explicit state approach toolmaker would say. Okay. Okay.
But I mean, in generally, like symbolic is generally just better.
Yeah, I think there's been more research in that area, and there is, yes, you know, with the inductive techniques and abstraction techniques that all work in with symbolic model checking. I think certainly the research interest in symbolic model checking has been enormously more. Okay. And that's partly probably because there's also a lot of success in practice. Yeah. So are you guys willing to, how long are you willing to stay for another 10 minutes? Yes or no? For this you have to answer. I guess I won't hold it against you if even one person says no. So I assume that is a yes answer, okay? Okay, so illustration with fairness. I will introduce this and I will end there. So what happens? See, this picture is a little bit more detailed picture of for what happens when you do EG of F using clean iteration. Starting from true, you iterate by removing states that should not be. I mean, by removing states that on which, yeah, so that either lead to things that are going outside to a state in which you know, none of its successors F is true. So you end up with what you end up at the fixed point is a representation of states that are connected in this fashion here. Okay, they all have these loops. See, what fixed point computes is a symbolic representation of these states. Obviously, I'm showing it as in an explicit form. Okay, and your explicit state algorithm was also exploiting this fact that everything has to end up in a strongly connected component with tails, prefix tails like like this. So that's what your here also you will end up. Your formula ends up representing these states. Okay, that's clear, no? So yeah, why am I showing this? For two reasons. Okay, but nonetheless, the point that someone raised and which I concurred with still remains that it can remove, in this case, removal, a lot of these states that should not be in there. In each step, it can remove a whole, lots of them. Okay, but that aside, eventually, this is what your representation is. So why am I showing this? If you had a fairness constraint of this form, then I mean these kinds of kind of parts that you, I mean these kind of structures that you have that you end up there, some of them could be fair, some of them may not be fair, and that's what I have shown here. So for example, this is obviously fair because it has a p state as part of that. And this one, the one with the self loop here, is not fair because not of p is not true there. So one observation that you can make is for the EGF case, every state, if there are states from which, yeah, so you have to have you should remain there are states from which F continuously holds. If you did not have fairness constraints, F just continuously holds. Here you have to have an additional constraint that F has to continuously hold until not P holds, okay? Until P holds for each of the fairness constraints defined in the sets, okay? And that's what you'll have to. So in addition to removing those states in which, not F, F is never, these states in which F never holds, you will have to enforce this constraint as well. And that's what is done. So the constraint is, it's probably stated here, if you have fairness constraints here, what should tau Z be characterized as? All states in Z satisfy F, of course. That is the usual EGF constraint. But for defining the fair version of it, the path formed by the states in Z must be fair. What does that mean? That is, for every state S belonging to Z, there must exist a sequence of F states whose length is greater than or equal to 1 to a state in Z that satisfies every a state in every pk, for k is equal to 1 to n. So this part, the second bullet, can be expressed as a E until constraint. This is exactly. So in addition to, earlier we just had Ex of F and Ex of Z, okay? So what was there here was just Z, Ez was here. Now here you will have to say, those Zs that I have to keep there must be such there is a prefix, a sequence of states that lead to something in which at least, for each of the PIs, one, that this should be true. There's something that's missing. Yeah. Correct. So here you see there is a big conjunction here. Okay. There's one conjunct in that conjunction of this form for each of the PIs, because that's how fairness constraint is defined. That one state, any state from each of the PIs must be included. And that's what this thing is does. So just changing your tau to this form, which includes another nested CTL, the EX with an EF nested in there, will define the set of all states in which EF of GFF is true. The steps after this, that you require, modification steps remain the same as before in the explicit state model checking. You define a special predicate called fair, okay, which is equivalent to EF of G is true. Okay, that's exactly, you express the EF of G, and EF of G is defined this way. When checking fair versions of EX and fair version of EF until is done by checking, by adding that fair predicate in here, where fair is defined this way. Okay, so I'll stop here. This is something that will require you to stare at it a little bit more and then read. So it's also there in the book. So if you have any questions, I know that it's the end of the day. So you yeah, if you have some small questions, I can take, but it's already 5. So any questions? Okay, thanks again. I'll see you Thursday.
Hello.
Yeah, hello.
Yeah, so I'm sorry, I lost internet connections for a couple of seconds there. So
No. I was just saying if there are asked if there are any questions. If not, we'll call it a day. That's what I said.
okay.